Now let's do some example. It is a past lecture example, and I modified a little bit such that you need to do some sketch of distribution of average shear stress. A simply supported beam is under an external transverse load P applied in the midsection. Sketch the shear force diagram along the length of the beam as well as the shear stress distribution along the length of the beam for points A, O, and B. So it is talking about the points of A, O, and B of the cross-section. Probably there is some overlap of use of letters, so bear in mind with that. So A and B in the left figure is talking about the tips, the pin and the roller support, while the AOB in this cross-section is talking about a point in the cross-section. Besides, we also need to sketch the distribution of average shear stress along the transverse direction of the cross-section. First, we try to sketch the shear force diagram along the length of the beam, which is very easy. If we cut the beam between 0 and L/2, so we cut the beam here, then by sign convention of the beam, the shear force inside the beam is Vx equals to P divided by 2, because it is significant that the two supports are both given the load of P/2. So for the left section, the Vx is P/2, and if we cut the beam on the right hand half like this, then the shear stress inside the beam will become minus P divided by 2. Then we can sketch the shear force diagram along the length of the beam like this. It is quite simple. Next, you are required to sketch the shear stress distribution along the length of the beam for those 3 points. So the second moment of inertia of this cross-section, which is very easy to compute, we compute a lot of times in the previous tutorials. It is given by the width times the height cube divided by 12. The width of the cross-section at any position is given by W. Because it is rectangular beam, the width is uniform across the vertical direction. In the previous slide, we found that the distribution of shear stress is given by P divided by 2 for the left half and minus P/2 for the right half. So at this moment, we confirmed 3 items. One is the second moment of inertia, another one is the width, another one is the shear force applied in this cross-section. So we confirmed those 3 quantities. Recall that our equation is tau equals to Vq divided by Iw. So what we need to do now is to determine what is Q. However, what I want to tell you is that in this tutorial, the quantity Q is one of the most important, one of the key factors for the determination of the shear stress. In this example, you will see at point A, we only compute the region above it. So still recall that just now, when we derived the formula, what is our lower and upper limits? And after we find the first moment of inertia, what is the shear stress we found? The shear stress we found is actually the shear stress at the level of y, right? Y is here. And what is the first moment of inertia we found? The first moment of inertia is just the region above the level of y. So now at point A, y equals to h divided by 4 and y2 equals to h divided by 2. Then the first moment of inertia evaluated for this region with respect to the neutral axis is given by q equals to the double integral of y dA, but dA equals to dy from h/4 to h/2, and the dz is equal to w. So what I mean is that the width, no matter where you take the integral, will always be w. So actually you can take this thing out to be w. Then we compute this first moment of inertia, and we get 3wh squared divided by 32. Actually, still remember that in the previous tutorial, we didn't use the integral to find the first moment of inertia. Actually, for the rectangular region, there is another way to find the first moment of inertia, which is we first find its area. So the area of this shaded region, the region of interest, is given by WH divided by 4. Then we try to find the distance between its axis of symmetry and the neutral axis. So for this region, its axis of symmetry has a distance of 3h divided by 8 with respect to the neutral axis. Then it is 3h divided by 8. By multiplying those two terms together, you will also get the same answer, which is 3wh squared divided by 32. At point O, rather similar. First, you find its area, which is wh divided by 2. Also, the axis of symmetry of the shaded area has a distance of h divided by 4 with respect to the neutral axis. Therefore, the first moment of inertia of the shaded area is given by wh squared divided by 8. At point B, the area is given by 3wh divided by 4, and the distance of the axis of symmetry of the shaded area with respect to the neutral axis is given by h divided by 8. The first moment of inertia is given by 3wh squared divided by 32. So just now we determined V, I, and W as well as Q. Then the average shear stress at the level of A, level of O, and the level of B can be found by using the shear formula. Still recall that the shear stress found in this way is an average across the width. So across the width, there could be a parabolic distribution as shown in the previous slide, okay? So it is just an average. Recall that, it is just an average. After that, for point A, we found the average shear stress when V is positive is given by 9p divided by 16wh. At point O, it is given by 3p divided by 4wh. And at point B, it is given by 9p divided by 16wh. Finally, we can draw the distribution of shear stress along the length of the beam. For point A, first it is 9p divided by 16wh, but after L divided by 2, the shear force V will become minus, then consequently the shear stress inside it will become minus as well. This is why, for the first half, for the left half of this beam, the shear stress is positive, which is 9p divided by 16wh. But for the right half, the shear stress is negative, which is minus 9p divided by 16wh. And similar for O and B. Next, we are required to sketch the distribution of average shear stress along the transverse direction of the cross-section AA, which is located at the left half of this beam. Now we have V, I, and W are all constant. Then the first moment of inertia of a region above a point located at an arbitrary altitude y is given by this. So how can we get that? So consider a piece of shaded area. This cross-section has a width of w and a height of h. This is the neutral axis, which means the upper end is given by h divided by 2 and the lower end is given by minus h over 2. The position of the axis of symmetry of this shaded area is given by y plus h divided by 2 divided by 2. So it is written here. The height of the shaded cross-section is given by h minus 2 divided by y. It also has a width of w, which means the area of the shaded region is given by h divided by 2 minus y times w. So multiplying all those things together, we can get the first moment of inertia of the shaded region with respect to the neutral axis, which is w times h divided by 2 minus y times 1/2 of h divided by 2 plus y. Since the moment of inertia is given by wh cubed divided by 12, we substitute this value or first moment of inertia into our shear formula, which is located here, here, and here. So notice that we absorbed w and 1/2 into this term. Now we do some cancellation regarding to the shear formula. We know that this w can be cancelled with this w. Then the denominator only has wh cubed remaining. But we know that the cross-sectional area of this cut surface is given by wh, which means we can rewrite the wh cubed to be ah squared. Then we further simplify this expression by taking h squared divided by 4 out from this bracket. Then we get the result, which is 1.5 times v divided by a times 1 minus 4y squared divided by h squared. So what does that mean? V divided by A is the average shear stress acting on the cross-section. The maximum shear stress occurred on the neutral axis. The reason is that in order to maximize this equation, we want to make this term to be 1, and the only way that we can do that is to make y equals to 0. The magnitude of the maximum shear stress is 1.5 times of the average value, as what we can observe from this formula. Also, since the average shear stress in the transverse direction is a function of y, and we observe that y is quadratic, therefore we conclude that the distribution of the shear stress is parabolic along the transverse direction. This is actually a concept introduced in the textbook and your lecture notes. You can find the distribution of the shear stress here. So this is the distribution of the shear stress inside the beam along the transverse direction, and it is parabolic and is given by this equation.